Today we explain the next point, electric flux. In that article, firstly we explain the lines of force or electrical field lines. Then we see what are the properties of the lines of force, and using that lines of force concept, we explain the electric flux through a closed surface. Now the first point we discuss here about the electric field lines or the lines of force. The concept of the electric lines of force was first introduced by Faraday, which gives the representation of the electric field. In that electric field, if we draw a path which is followed by an electric charge, that path is nothing but electric lines of force. Hence, the electric lines of force or the field lines is defined as it is the path which is followed by an electric charge free to move in an electric field. Such an electric field lines around some charge configuration is shown here. If we are considering the positive charge, that positive charge, the electric field lines around the positive charge is represented by the straight lines which are originating from the charge. Secondly, if we are considering the negative charge, that charge also surrounded the electric field lines. That electric field lines due to negative charge are represented by the straight lines, and all that lines are terminating towards the charge. In the third case, if we consider two like charges, whether positive positive or negative negative charges, the field lines around that system which indicate the mutual repulsion between them, that lines are directed away from the two charges, means they are repelling with each other. And in the last case, if we are considering the electric field lines around the configuration of two equal and opposite charges, this is just like a dipole. It shows the mutual attraction between the charges. These lines of force satisfy the different properties. Hence, we have to see what are the properties of the lines of force. Now, what it shows from that figure, the first point we note, this is the one of the property of the line of force. They are continuous, smooth curves without any break. Secondly, we note here, if the tangent drawn to a line of force at a point, it gives the direction of electric field at that point. Third property we note, they cannot form a closed loop. That is shown if we considering the two unlike charges, how they behave. They do not form any closed loops. Next property we note, the two lines of force cannot cross with each other. That is not shown here. That cannot cross with each other. Nextly, the lines of force are always perpendicular to the surface of the conductor. Means all the lines directed normally to the conductor. Means these are perpendicular to the surface of the conductor. The lines of force do not pass through the conductor because the electric field inside the charged conductor is zero, and due to that reason the lines of force do not pass through the conductor, but they must pass through the insulator, since electric field inside the insulator is not zero. As the lines of force are closer and crowded at a point, then what it shows, this is last figure, we say the lines of force are closer and more crowded at a point. At that point, the intensity of the field is large. On the other hand, if they are apart and less crowded, at that point the intensity of field is less. Now these are the various properties of the electric field line or the lines of force. The next we explain what is the electric flux. Electric flux is the property of a vector field. That vector field example, we take electric field. Electric field is a vector quantity and therefore it is the property of electric field also. Now how we define the electric flux? The total number of electric field lines that we show earlier. Total number of electric field lines when passing normally through a given surface area in the unit time, it is known as electric flux. Now how we calculate the electric flux? If we suppose a given plane has surface area S and that plane is normal to the direction of the flow of uniform electric field lines, then the total flux is the product of the field intensity, electric field intensity or the electric field multiplied by surface area. Now we considering that case. Now how we calculate the electric flux? If that flux is passing normally through a given plane whose surface area is very small. All straight line shows electric field lines which are targeted towards the surface whose area is very small, delta S. Then it shows here the normal drawn to that plane is in the direction of external electric field lines, means theta is 0. And if theta is 0, then the electric field component is simply E. Hence, through the small surface element delta S, the electric lines passes normally through the small surface element is del phi equal to E into ds. But in the other case, secondly, if the electric field lines are tilted at some angle with the normal drawn to the small surface element delta S. Therefore, that electric field lines which makes component along the direction of the normal, and that component is E cos theta. In that case, now what is electric flux that we calculate here? As the lines are tilted at an angle theta, The component of the electric field normal to the small surface element ds is E cos theta. Hence, according to the definition, normal component of electric field line multiplied by surface area of a given plane. Normal component is E cos theta into surface area, small surface element is delta S, and you know E cos theta delta S. It is the dot product of the two term vector E dot vector ds. And the dot product of the two term is electric flux, small electric flux through the small surface element, and it is a scalar. That is, we have to write in the next step. Hence, this is for small surface element. If we are considering a closed surface, that is S, and that surface is divided into number of small surface elements delta S1, delta S2, delta S3 up to so on delta Sn. At each element, the corresponding electric field lines is in the direction of E1, E2, E3 up to the En. Then how we calculate the electric flux, the total electric flux for a closed surface? Yes. Initially we take the sum of all components of the electric flux at each and every small element. For the element delta S1, the electric flux is delta phi 1 plus delta phi 2 plus delta phi 3 up to delta phi n. Delta phi is for first element E1 vector E1 dot delta S1 plus E2 dot delta S2 up to the En dot delta Sn. Instead of all those addition terms, we take one term in terms of summation I equal to 1 to n vector E dot delta Sn. Hence, for closed surface, that equation we again write in terms of the closed surface, integral over the closed surface equal to phi equal to integral E dot ds for closed surface. Hence, electric flux that we calculate here is found to be a scalar quantity. It is scalar quantity. Secondly, we find what is the unit of electric flux. We defined earlier the definition of the electric flux. If a plane is normal to the flow of the uniform electric field lines, the total flux is the product of electric field lines multiplied by surface area. Hence, unit of E and unit of surface area is known, then we get the SI unit of electric flux. Electric field lines or electric field unit is Newton per Coulomb, that we discussed in the first earlier lecture, multiplied by surface area. What is the unit of surface area? Meter square. Hence, the resulting term becomes Newton meter square per Coulomb. Or if unit of electric field we defined earlier, it is volt per meter. Then in terms of volt and meter, what is the SI unit? Volt per meter multiplied by meter square. Then it becomes volt meter. And that is the term which come under electric flux. Hence, remember what is electric flux? Electric flux, which is defined as The total number of electric lines of force passing through a given area in the unit time gives electric flux, and it is measured in terms of Newton meter square per coulomb or volt meter, and it is a scalar quantity. Thank you.